Picture this: a universe so vast and enigmatic, it holds secrets that defy everything we think we know about reality. Out there, beyond the familiar glow of stars and planets, lies a cosmic playground where the rules of physics twist into impossible shapes, where black holes might be gateways to other dimensions, and where entire civilizations could exist in forms we can't even begin to comprehend. Space isn't just empty darkness, it's a treasure chest of mysteries waiting to crack open our understanding of existence itself. And today, we're diving headfirst into the rabbit hole of the most bizarre space theories ever proposed, ideas so wild, they'll make you question whether reality is even what it seems. What if I told you that somewhere in the cosmos, time runs backward, or that our entire universe is just a holographic projection? These aren't plot twists from a sci-fi novel. They're real theories backed by some of the brightest minds in astrophysics. From the haunting possibility that we're living inside a black hole to the spine-tingling idea that dark matter could be an invisible, parallel universe brushing against ours, the cosmos is stranger than any fiction. And the deeper we look, the more we realize how little we truly know. Every discovery peels back another layer, revealing questions that seem to multiply faster than answers. This video isn't just a list of far-out ideas, it's a journey to the edges of scientific imagination, where logic bends and the impossible starts to feel plausible. We'll explore 30 of the most mind-bending space theories that challenge reality itself, each one more astonishing than the last. Whether it's the eerie notion that the universe is conscious or the jaw-dropping concept that we might be alone in an infinite void, these theories don't just reshape how we see the cosmos, they reshape how we see ourselves. So buckle up, by the time we're done, you might never look at the night sky the same way again. What if everything around us, the stars, the planets, even your own thoughts, weren't real? Not in the way we assume, at least. This is the unsettling premise of the simulation hypothesis, the idea that our entire universe might be nothing more than an ultra-advanced computer program designed by a civilization so far beyond us, their reality makes ours look like pixels on a screen. Think about the video games we play today, where entire worlds exist in code. Now imagine a future where those virtual worlds become indistinguishable from reality. That's the core of this theory. We might already be living in someone else's creation. Prominent figures like Elon Musk and philosopher Nick Bostrom have lent serious credibility to this idea. Musk famously claimed the odds we're living in base reality are 1 in billions, while Bostrom's simulation argument breaks it down mathematically. If future civilizations could run ancestor simulations, digital recreations of their own past, then statistically, it's far more likely we're inside one of those simulations than the original universe. Even some physicists entertain the possibility, pointing to odd quirks in quantum mechanics where particles behave like they're being rendered only when observed, almost like a video game optimizing processing power. But what would that mean for us? If we're just lines of code, do our choices even matter? Some argue it wouldn't change much. Pain, joy, and discovery would still feel real to us. Others see it as profoundly isolating, like realizing you're a character in a story with no author. Critics push back, of course. They say there's no direct evidence that consciousness can't be replicated digitally, or that the energy needed to simulate an entire universe defies plausibility. Yet the eerie possibility lingers. After all, if a simulation is flawless, would we ever know? The deeper we dig into reality's true nature, the more it feels like staring into a mirror, only to wonder if the reflection is the only thing that's real. The universe as we know it, vast, expanding, filled with galaxies, might not just be floating in empty space. It could be trapped inside the crushing depths of a black hole, an unimaginably dense cosmic prison from which nothing, not even light, can escape. This mind-bending idea, known as the black hole universe theory, flips our understanding of reality on its head. What if the Big Bang wasn't the beginning of everything, but simply the violent birth of our universe from the wreckage of another? Physicist Nikodem Poplawski is one of the leading voices behind this theory. He suggests that when matter gets sucked into a black hole in some larger parent universe, it doesn't just vanish into oblivion. Instead, it might be crushed to an extreme density before rebounding outward in a massive explosion, a process eerily similar to the Big Bang. In other words, every black hole could be the seed of a brand new universe hidden inside its unfathomable depths. Our entire cosmos, with all its stars, planets, and mysteries, might just be one of countless others bubbling away inside the bellies of black holes we can't even see. This idea doesn't just rewrite cosmic history, it could solve some of astronomy's biggest puzzles. Take dark energy, the mysterious force causing the universe to expand faster and faster. If we're inside a black hole, that acceleration might not be some strange, unexplained energy. It could just be the natural stretching of space as matter continues to fall into our parent black hole from the outside. Even the cosmic microwave background, the faint echo of the Big Bang, might carry imprints of that original black hole structure, like fingerprints on the walls of our universe. But how could we ever prove something so wild? Some researchers point to the way black holes spin our universe shows a surprising preference for certain directions on the largest scales, a possible relic of inheriting its parent black hole's rotation. Others suggest studying the way galaxies cluster might reveal hidden geometric patterns left behind by the black hole's crushing gravity. Of course, skepticism remains. Critics argue there's no direct way to observe a parent universe, making the theory tough to test. But in a cosmos where time bends, particles teleport, and invisible matter outweighs the visible, maybe the most outlandish ideas are the ones we should take seriously. After all, if our universe really is nested inside something bigger, it raises a chilling question. What else is out there, lurking beyond the event horizon we can never cross? What if the world around you, the chair you're sitting on, the device in your hand, even your own body wasn't truly three-dimensional? What if it was all just an incredibly convincing illusion, like a hologram projected from the edges of the universe? This is the startling premise of the holographic principle, a theory that suggests our reality, with all its depth and solidity, might actually be encoded on a vast, flat surface at the cosmic horizon. It's not science fiction, it's a serious idea born from the collision of quantum mechanics and black hole physics, one that could rewrite everything we know about space, time, and the fabric of existence. The roots of this theory trace back to the work of physicist Leonard Susskind in the 1990s, building on earlier discoveries about black holes. Scientists had realized that when matter falls into a black hole, the information it carries doesn't just disappear. It somehow gets imprinted on the black hole's event horizon, the point of no return. This revelation led to a bizarre realization. All the complexity of objects swallowed by a black hole could theoretically be represented in two dimensions, like data stored on a celestial hard drive. Susskind and others took this further, proposing that if a black hole's interior could be fully described by its surface, maybe the entire universe operates the same way. Here's where it gets even wilder. If the holographic principle is true, every event, every particle, every force we experience in our three-dimensional world is just a projection from a two-dimensional boundary at the edge of the cosmos. Imagine watching a movie on a screen. The images seem deep and lifelike, but they're really just flat pixels arranged in a specific way. Our universe might work the same way, with the true source code of reality existing on a distant, flat surface we can't even see. This isn't just philosophical musing, it's a concrete framework that could solve one of physics' biggest problems, uniting Einstein's theory of gravity with quantum mechanics. Quantum gravity has long been the holy grail of theoretical physics, and the holographic principle offers a tantalizing path forward. In this view, gravity isn't a fundamental force but an emergent phenomenon, a side effect of how information is encoded and processed on that two-dimensional boundary. It's like realizing the images on your TV don't actually move. They're just a clever arrangement of static dots that create the illusion of motion. If correct, this could explain why gravity feels so weak compared to other forces. It's not a true force at all, just a shadow of deeper processes playing out on the universe's edge. But how could we ever test such an abstract idea? Surprisingly, some experiments hint at its plausibility. Studies of high-energy particle collisions suggest that the amount of information in a region of space doesn't scale with its volume, as you'd expect in a 3D world, but with its surface area, just like the holographic principle predicts. Even the fabric of spacetime itself might be pixelated at the tiniest scales, a digital-like structure that aligns with the theory's core ideas. Of course, not everyone's convinced. Skeptics argue that the math is still speculative, or that the principle might only apply in extreme environments like black holes, not the universe at large. Yet the implications are too profound to ignore. If the holographic principle is true, it means reality is far stranger than we ever imagined. The solid, tangible world we experience could be nothing more than a cosmic mirage, a projection from a realm we'll never directly observe. It challenges our most basic assumptions about existence. What if depth, distance, and even time are just illusions, artifacts of how our brains interpret a deeper, flatter truth? Whether this theory holds up or not, one thing's certain: the universe is far weirder, far more mysterious than we could have ever guessed, and that's just the beginning of the rabbit hole. Imagine floating in an endless void, utterly alone, with no stars, no planets, just darkness stretching forever in every direction. And then, out of nowhere, a flicker of thought sparks into existence. You wake up, your memories click into place, a world forms around you, your childhood, the faces of loved ones, everything seemingly real. But here's the terrifying catch: none of it actually happened. You're a Boltzmann brain, a self-aware consciousness conjured from pure chance by random quantum fluctuations in the emptiness of space. This isn't just a sci-fi nightmare, it's a real paradox born from the laws of thermodynamics, one that threatens to unravel our most basic assumptions about reality and our place in it. The idea traces back to Ludwig Boltzmann, a 19th-century physicist who revolutionized our understanding of entropy, the universe's tendency toward disorder. He realized that in an infinite cosmos, even the most improbable events must happen eventually, given enough time. That includes the spontaneous assembly of atoms into a fully functioning brain, complete with fabricated memories and a convincing illusion of reality. In this scenario, you wouldn't be the product of billions of years of evolution on a stable planet, but a fleeting accident in the cosmic dark. The odds are astronomically low, but in an eternal universe, probability demands it happens countless times, in fact. What makes this theory so unsettling isn't just the science, it's the philosophical quicksand it drags us into. If Boltzmann brains are possible, how do we know we're not one? After all, a brain that randomly forms would have no way to tell the difference between real experience and an elaborate hallucination. The math suggests these random consciousnesses would vastly outnumber real observers like us, meaning statistically, you're probably one of them. Cosmologists recoil at this implication. It would make all scientific observation meaningless, since the data we collect could just be part of the illusion. Some physicists fight back, arguing that our universe's specific conditions, its relatively low entropy at the Big Bang, the precise tuning of physical constants, make Boltzmann brains vanishingly unlikely. Others propose we live in a multiverse where most regions are dead voids, making our structured reality a rare exception. But the paradox lingers like a shadow, forcing us to confront a brutal question. If reality can be faked by pure chance, what can we ever truly trust? The answer might lie not in denying the possibility, but in recognizing something profound: that consciousness, whether born of atoms or accident, is the only lens through which reality can ever be known. In a universe stranger than fiction, maybe that's the only truth we can hold on to. Black holes suck everything in: light, matter, even time itself. But what if there's a cosmic opposite, a place where reality violently erupts outward instead of collapsing inward? Enter white holes, the universe's hypothetical exhaust valves, spewing out energy and matter with such force that nothing can ever enter them. While black holes are cosmic vacuum cleaners, white holes would be fire hydrants blasting reality into existence, a one-way street where the universe only pours out, never takes in. The math of general relativity actually allows for white holes to exist. They're not just science fiction. They emerge as legitimate solutions to Einstein's equations, playing by the same cosmic rules as black holes but running the script backward. Imagine a black hole in reverse. Instead of an event horizon trapping everything inside, a white hole would have an event horizon that only lets things escape, ejecting matter and energy in a torrential outburst. Some theories even suggest every black hole might be connected to a white hole through a tunnel in space-time, a wormhole creating a bridge between 2 points in the universe, or even between 2 different universes. But here's where it gets truly mind-blowing. Nobel Prize-winning physicist Roger Penrose proposed that a white hole might not just be a distant curiosity, it could be the very origin of our universe. His conformal cyclic cosmology theory suggests that the Big Bang itself was a white hole, the explosive endpoint of a previous universe's collapse into a black hole. In this model, universes don't just die, they recycle. When one universe reaches its maximum entropy and fades into darkness, all that compressed matter and energy rebounds as a white hole explosion, birthing a brand new cosmos. Think of it like a cosmic phoenix. A black hole in a parent universe crunches down to an unfathomable density until bang. It erupts as a white hole, becoming the seed for another universe's Big Bang. This would mean our universe isn't the first and only one, but part of an endless chain, each iteration emerging from the ashes of the last. Penrose even claims to have found evidence in the cosmic microwave background, patterns of concentric circles that he interprets as gravitational echoes from previous universes. Of course, not everyone's convinced. Critics argue that white holes violate the second law of thermodynamics, since they'd seemingly create order from chaos. Others point out that we've never observed one, suggesting they might be mathematical quirks rather than real cosmic objects. But if they exist, white holes could solve one of physics' biggest mysteries: what happened before the Big Bang? Instead of a singularity emerging from nothing, we'd have a natural, cyclical process, an infinite loop of creation and destruction, where every ending is just a new beginning in disguise. Whether white holes are real or not, they force us to confront a staggering possibility. If Penrose is right, then every star, every planet, every one of us might just be the echoing aftermath of another universe's death throes. The cosmos could be an endless spiral of rebirth, where black holes aren't tombs but cosmic wombs giving birth to realities we can't even begin to fathom. And if that's true, the universe isn't just stranger than we imagine, it's stranger than we can imagine. What if nearly 300 years of human history never actually happened? Not just forgotten or misrecorded, completely fabricated, an elaborate fiction woven into the timeline to serve powerful agendas. That's the spine-chilling claim of the phantom time hypothesis, a theory that argues the period between 614 and 911 AD was invented out of thin air. According to this idea, rulers and religious leaders conspired to insert these phantom centuries into the historical record, altering documents, forging artifacts, and even manipulating celestial observations to create the illusion of time that never was. If true, it wouldn't just rewrite history books, it would shatter our understanding of astronomy, archaeology, and the very fabric of time itself. The theory's most vocal proponent, German historian Heribert Illig, didn't pull this idea from nowhere. He pointed to glaring inconsistencies in the historical record during this period. architectural styles in Europe show suspiciously little evolution across these centuries, as if time stood still. Key astronomical events documented in chronicles, like solar eclipses, don't align with modern calculations when projected backward. Even the Gregorian calendar reform in 1582, which corrected a 10-day drift in the Julian calendar, suggests a discrepancy that some argue only makes sense if hundreds of extra years were secretly added. But the implications go far beyond missing buildings or misstated kings. If the phantom time hypothesis were true, it would throw carbon dating, one of science's most trusted chronological tools, into chaos. Radiocarbon dating relies on predictable decay rates of carbon-14 isotopes, calibrated against known historical events like tree rings or volcanic eruptions. Remove 3 centuries from that timeline, and suddenly, artifacts dated to this period would be wildly off, like a clock missing its gears. Entire layers of archaeological findings would have to be reinterpreted, with objects declared medieval, potentially belonging to entirely different eras. Astronomy faces an even sharper paradox. Ancient star maps and planetary observations from China, the Middle East, and Europe during this phantom period align too precisely with modern simulations to be mere forgeries. If these records were fabricated, the conspirators would have needed an impossible grasp of celestial mechanics centuries ahead of their time. Critics also highlight Byzantine and Islamic histories, which document events and rulers in meticulous detail during these supposedly non-existent years, histories that would require a globally coordinated fraud on an unimaginable scale. Yet the theory persists, fueled by unnerving gaps. Why does Charlemagne's empire, a cornerstone of this era, leave behind so few physical traces compared to his legendary influence? Why do some lunar eclipse records from the 9th century fail to match computational models unless those dates are shifted? The most unsettling question isn't whether the hypothesis is plausible, but what it reveals about how fragile our grip on history really is. Time isn't just a line, it's a story, and stories can be edited. Whether by error or design, the phantom time hypothesis forces us to confront a haunting possibility, that the past we take for granted might be built on riddles we haven't even thought to ask. Forget everything you've been told about gravity ruling the cosmos. What if the real architect of the universe isn't the silent pull of massive objects, but the crackling, dynamic dance of electric currents coursing through space? This is the radical premise of the electric universe theory, a fringe but fascinating challenge to mainstream cosmology that swaps black holes and dark matter for something far more tangible: plasma and electromagnetic forces that shape galaxies, stars, and even life itself. At the heart of this idea stands Hans Alfvén, a Nobel Prize-winning physicist who revolutionized plasma science in the 1960s. Alfvén discovered that space isn't the empty void we imagine. It's threaded with charged particles forming vast, invisible circuits. These currents, he argued, could sculpt cosmic structures with far greater precision than gravity alone. Picture lightning on a galactic scale, filaments of plasma stretching across light years, twisting into spirals that birth stars, or even forming the backbone of entire galaxy clusters. To Alfvén, the universe wasn't a static sculpture carved by gravity. It was a living, pulsing electrical network. Proponents of the electric universe take this further, suggesting that electromagnetism explains mysteries gravity can't. Why do galaxies rotate as if glued together, defying the pull of their visible matter? Mainstream science invokes dark matter, an invisible substance we've never detected. Electric universe theorists say the answer is simpler. Galaxies are wired into cosmic circuits, their motion driven by flowing currents. Even the sun, they argue, might not be powered by nuclear fusion alone, but by electric currents funneling energy from the Milky Way's plasma web. Some point to the sun's corona, mysteriously hotter than its surface, as evidence of this external power source. The theory's boldest claims, though, lie closer to home. Ancient myths worldwide describe celestial battles, gods hurling thunderbolts across the sky. Electric universe researchers interpret these as eyewitness accounts of planetary-scale electrical discharges, a time when Venus or Mars orbited nearer Earth, sparking apocalyptic lightning storms. They point to geological oddities like the vitrified stone forts of Scotland or the scarred surfaces of asteroids as potential fingerprints of these cosmic short circuits. Mainstream science pushes back hard. Critics argue that plasma physics can't replace gravity's dominance on large scales, or that the theory cherry-picks anomalies while ignoring overwhelming evidence for standard models. Yet the electric universe persists, fueled by its power to explain without invoking unseen dark matter or energy. Whether it's right or wrong, it forces us to question, have we underestimated the crackle of electricity in the silence of space? After all, if the cosmos runs on currents we're only beginning to map, reality might be far more shocking than we ever imagined. Time isn't a straight line or even a flowing river, it's a cube. At least, that's the explosive claim of the time cube theory, one of the internet's most baffling and bizarre cosmological ideas. Conceived by an eccentric electrical engineer named Jean Ray, this theory tosses out everything we know about clocks, calendars, and relativity, replacing them with a radical vision where 4 simultaneous days unfold at once, stacked like the faces of a cube. It sounds like the rantings of a sci-fi novel, but for years, Ray's feverish online manifestos and public lectures turned time cube into a cult phenomenon, blending cryptic diagrams with incendiary attacks on mainstream science. At the heart of the theory lies a geometric twist on time itself. Ray argued that Earth's rotation doesn't just create one-day night cycle, it spawns 4 distinct days happening concurrently, each occupying a different corner of the time cube. Morning, noon, evening, and midnight aren't phases of a single day but parallel realities all existing simultaneously. Picture a cube spinning in space. As one face tilts into sunlight, another dips into shadow, and the others hover in between. In Ray's mind, this wasn't metaphor, it was literal physics, a fundamental truth ignored by what he called educated, stupid academics. The implications get even stranger. Ray claimed that human perception traps us in just one of these 4 days, blind to the others. He insisted that our linear view of time is a lie, a mental prison enforced by schools and governments. His solution, a time cube calculator that would supposedly sync users with all 4 days at once, unlocking higher consciousness. Critics dismissed it as gibberish, but Ray's relentless online presence, complete with chaotic, all-caps rants and homemade animations, turned time cube into an early internet legend. It became a meme before memes had a name, a symbol of defiant anti-intellectualism wrapped in cosmic mysticism. What makes time cube fascinating isn't its scientific merit, it has none, but the way it exposes the thin line between genius and madness in the search for ultimate truth. Ray's riffs on sacred geometry, his tirades against single-day liars, even his cryptic slogan, 4 simultaneous 24-hour days spin as one, all tap into a deep human hunger to crack reality's code, no matter how unhinged the method. And in a weird way, his obsession with multidimensional time foreshadowed legitimate physics debates about parallel universes and nonlinear time, even if his conclusions were light years from peer-reviewed science. Time cube's legacy endures as a cautionary tale and a cultural artifact. It's a reminder that the universe invites wild speculation, but not all speculation leads to discovery. For every Einstein, there's a Jean Ray, a voice howling at the edges of understanding, convinced they've seen the shape of time itself. And while the cube may be fantasy, the longing behind it is real, to look beyond the clock and find time's true face, even if it's nothing like we imagined. You're in a life or death scenario, or maybe strapped into a twisted version of Schrödinger's cat experiment, where a quantum trigger decides whether you live or die. Now imagine this, every time the trigger fires, the universe splits. In one reality, you perish, but in another, you survive. And here's the eerie part: your consciousness only experiences the timelines where you keep breathing. This is the unsettling heart of quantum immortality, a theory suggesting that in a multiverse of infinite possibilities, your subjective experience might always skew toward survival, no matter how improbable. The idea springs from the many worlds interpretation of quantum mechanics, which argues that every quantum event spawns branching realities. Combine this with the observer effect, the notion that consciousness collapses quantum probabilities into a single outcome, and you get a bizarre consequence. From your perspective, you could never witness your own death. Every near-fatal accident, every brush with disaster, would simply shunt your awareness into a version of reality where you narrowly escape. It's not that you're invincible, it's that the you who dies ceases to experience anything, while the surviving you carries on, oblivious to the other timelines where things ended badly. The most infamous thought experiment illustrating this is quantum suicide. Picture a machine rigged to a quantum particle, maybe an atom, with a 50-50 chance of decaying within a minute. If it decays, the machine releases a lethal pulse. If not, you survive. In a single universe, you'd expect a 50% chance of death after each trial. But in the many worlds model, there's always a branch where the particle doesn't decay, and your consciousness follows that path indefinitely. To an outside observer, you'd appear impossibly lucky or cursed, depending on how you see it. Critics slam the idea as metaphysical sleight of hand. They argue it conflates subjective experience with objective reality, ignoring that most branches would still contain your corpse. Others point out that aging or disease would eventually make survival statistically absurd unless consciousness somehow hops to younger versions of itself in alternate realities. But proponents counter with eerie anecdotes, people surviving freak accidents against all odds, or near-death experiences reporting visions of sliding into parallel lives. Even if quantum immortality isn't literal, it forces a chilling question. How much of reality is shaped by the simple fact that we're here to observe it? The theory's deepest implication isn't about cheating death, it's about the nature of existence itself. If consciousness persistently follows paths where it endures, does that mean the universe is subtly structured to preserve observers? Or is it just a cosmic quirk, a side effect of infinite branching? Either way, quantum immortality blurs the line between science and philosophy, leaving us to wonder whether life is a fragile accident or a thread the cosmos refuses to let snap. The universe isn't just expanding, it's being pulled. Across unimaginable distances, entire galaxy clusters are streaming toward something we can't see, something so massive it warps the fabric of space itself from beyond the edges of our observable cosmos. Astronomers call this eerie phenomenon dark flow, and it's one of the most perplexing mysteries in modern cosmology. Imagine tossing a handful of leaves into a river. They should drift apart randomly with the current. But if every leaf suddenly started veering in the same direction, you'd suspect a hidden whirlpool lurking downstream. That's exactly what's happening on a cosmic scale, with thousands of galaxy clusters caught in a gravitational current they shouldn't even feel. NASA Wilkinson Microwave Anisotropy Probe first spotted the anomaly in 2008, analyzing the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature shifts in this radiation revealed something shocking. Clusters of galaxies millions of light-years apart were all moving in the same direction at breakneck speeds, some exceeding 2 million miles per hour. The kicker: there's nothing in our known universe big enough to tug them that way. No supercluster, no concentration of dark matter, just empty space stretching into infinity. Yet the pull is unmistakable, as if something colossal, something outside our cosmic horizon, is reeling them in. The most spine-tingling explanation. Another universe, not just a distant patch of our own cosmos, but a separate bubble of space-time entirely, lurking beyond the limits of what we can observe. In multiverse theories, other universes might float like soap bubbles in a higher dimensional foam, occasionally brushing close enough to exert gravitational influence. If one of these sibling universes happened to have radically different physics, maybe with stronger gravity or extra dimensions, it could be yanking on our galaxy clusters like a cosmic angler. Skeptics propose less exotic answers. Some argue the dark flow could be a statistical fluke, or that we're misreading the data due to incomplete sky surveys. Others suggest it's a remnant of the universe's violent birth, a primordial gradient left over from the Big Bang that set everything sliding in one direction from the very beginning. But the sheer scale of the motion defies these simpler explanations. The attractor would need to be hundreds of times more massive than the entire observable universe to exert this kind of pull, a scale that rewrites our understanding of gravity itself. Here's where it gets even stranger. If the dark flow is real and not some measurement error, it implies the universe extends far beyond what we call the observable portion, a region already 93 billion light-years across. Whatever's tugging these galaxies might lie tens or hundreds of billions of light-years further out, in realms we'll never see because their light hasn't had time to reach us. It's like standing on a shore watching waves roll in from a storm over the horizon. You can't see the tempest, but you know it's there by the way the water moves. The implications are staggering. If confirmed, dark flow wouldn't just hint at other universes, it would prove our cosmos is part of something infinitely larger, a structure so vast it makes our observable universe seem like a speck of dust in a hurricane. And that raises a humbling question. If we're being pulled towards something unimaginably massive, what else is out there just beyond the edge of sight? The answer might rewrite not just cosmology, but our very place in the grand scheme of existence. The silence is deafening. Across billions of galaxies, trillions of stars, and countless planets that should be teeming with life, we've found nothing. No signals, no spacecraft, no evidence of alien civilizations. This glaring contradiction between the universe's vast potential for life and our total lack of proof is the Fermi Paradox, and its solutions range from the unsettling to the downright terrifying. Take the zoo hypothesis. Imagine Earth as a cosmic exhibit, deliberately isolated by advanced civilizations who observe us like animals in a wildlife sanctuary. They've set up invisible boundaries, maybe cloaking technology or undetectable monitoring systems to ensure we develop without interference. It's not entirely far-fetched. After all, we enforce similar rules for uncontacted tribes or fragile ecosystems. The prime directive from Star Trek mirrors this idea. Don't intervene until a species reaches a certain technological maturity. But if this hypothesis is true, it raises a chilling question. What happens when we finally graduate? Do we join the galactic community, or are we forever destined to be lab rats in someone else's experiment? Then there's the darker alternative predator civilizations. What if the reason we haven't heard from aliens is because the ones who make noise don't last? In this scenario, the universe is a cosmic jungle where advanced species stay hidden to avoid attracting the attention of something far worse. Think of it like the dark forest theory from sci-fi. Every civilization is a hunter hiding in the trees, terrified of revealing its location. Broadcasting signals could be the equivalent of shouting in a forest full of wolves. Even our own history shows the peril of first contact. Indigenous cultures devastated by more technologically advanced invaders. If that pattern holds universally, silence isn't just golden, it's survival. Or consider the quarantine hypothesis. What if we're not just isolated but locked away for our own protection, or everyone else's? Maybe our violent tendencies or unchecked pollution make us a threat to the galactic ecosystem. Advanced civilizations might have imposed a cordon sanitaire around our solar system, preventing us from spreading until we evolve past self-destruction. There's precedent for this too. When NASA sterilized spacecraft visiting Mars, it wasn't just about protecting potential Martian life. it was about containing our own biological contamination. Now scale that up to a civilization-wide containment protocol, and these are just the intentional explanations. Others argue the paradox might have simpler, bleaker answers. Perhaps intelligent life is vanishingly rare, or self-annihilation is the inevitable endpoint of all technological progress. Maybe we're early to the party, born in a cosmic quiet before the real symphony begins. Each possibility forces us to confront uncomfortable truths about our place in the universe, our future, and whether we're truly alone. The eerie silence isn't just a puzzle, it's a mirror reflecting back our deepest hopes and fears. The Big Bang wasn't the beginning, it was just the latest reboot in an endless cycle of cosmic destruction and rebirth. This is the spine of the Big Bounce theory, a radical alternative to the idea of a one-and-done universe. Instead of a fiery singularity erupting from nothing, this model proposes that our cosmos is trapped in an infinite loop, expanding, contracting, and exploding anew like a phoenix perpetually rising from its own ashes. The beauty of the Big Bounce lies in its symmetry. Picture the universe as a cosmic accordion stretching outward until dark energy's push weakens, then collapsing back under gravity's pull. At the moment of maximum crunch, all matter and energy compress into an unfathomably dense seed, hotter than anything in existence. But instead of disappearing into a singularity, quantum effects kick in, creating a repulsive force so powerful it triggers another explosive expansion. Boom! A new universe is born from the corpse of the old one, inheriting its physics but not its memories. No creator required, no edge of time to explain, just an eternal rhythm of death and resurrection. This isn't just poetic imagery, the math actually works. Loop quantum gravity, a leading theory attempting to unite quantum mechanics and general relativity, suggests spacetime isn't infinitely divisible, it's made of tiny, indivisible grains. At the Big Crunch, these grains resist further compression, causing a quantum rebound that could birth a new cosmos. It's like trying to crush a spring push hard enough, and it snaps back with even greater force. But there's a catch: entropy. The second law of thermodynamics states that disorder in a closed system always increases. If each cycle adds more chaos, wouldn't future universes grow progressively more disordered? Some theorists solve this by suggesting entropy resets at each bounce, while others propose that dark energy dilutes it across ever larger volumes. Roger Penrose's conformal cyclic cosmology takes a different approach. His model allows entropy to persist, but stretches spacetime so thin during the infinite future that particles lose all sense of scale, effectively resetting the universe without a true singularity. Penrose's vision is even stranger. In his model, universes don't bounce, they morph. As one epoch ends, its black holes evaporate via Hawking radiation, leaving behind nothing but massless particles floating in an endless void. At this point, the universe becomes mathematically identical to a high-energy Big Bang state, and the cycle begins anew. He claims to have found evidence in the cosmic microwave background, circles of anomalous temperature that could be gravitational echoes of collisions between supermassive black holes from a previous universe. Critics pounce on these ideas. If entropy isn't reset, wouldn't each cycle grow longer and colder, making life increasingly improbable? Others argue that quantum repulsion at the Big Crunch remains speculative, or that Penrose's circles could be statistical flukes. But the Big Bounce persists because it solves one of cosmology's deepest puzzles: what came before? No need for divine intervention or multiverses, just an infinite reel of cosmic history, each frame overwriting the last. After all, if time is a loop, perhaps we've had this conversation before, and will again when the next universe wakes up. Our universe might be sitting on a ticking time bomb, not made of matter or energy, but of the very fabric of reality itself. This is the nightmare scenario known as false vacuum decay, a phenomenon where the seemingly stable laws of physics could suddenly unravel in a cataclysmic chain reaction. Think of the cosmos like a frozen lake on a winter's day. It looks solid, dependable until one tiny crack spreads with terrifying speed, shattering the entire surface. Right now, we might be standing on that ice without realizing how thin it truly is. The heart of this theory lies in quantum field theory, which describes the universe as a patchwork of invisible energy fields. These fields determine everything from the mass of particles to the strength of gravity. Scientists believe our universe exists in what's called a false vacuum, a temporary low-energy state that seems stable, but isn't the absolute lowest possible energy configuration. It's like a ball resting in a shallow dent on the side of a mountain. A nudge could send it rolling downhill, and the moment it does, the rules of reality as we know them would rewrite themselves. Here's where it gets apocalyptic. If a random quantum fluctuation or worse, a high-energy physics experiment created a microscopic bubble of true vacuum somewhere in space, that bubble would expand at the speed of light. Inside it, the fundamental constants we rely on would change instantly. Atomic bonds might dissolve, gravity could invert, the very structure of matter might cease to exist in any recognizable form. The shockwave wouldn't just destroy stars and planets, it would erase the building blocks of existence faster than any signal could warn us. One moment, everything's normal. The next it's over. You might wonder, how real is this threat? Some physicists argue the Higgs field, which gives particles their mass, could be the culprit. Its measured energy level appears suspiciously close to the tipping point between stable and metastable. CERN Large Hadron Collider has even searched for signs of Higgs-induced vacuum decay, though thankfully no red flags yet. Others counter that if the universe were this fragile, 14 billion years should have been enough time for a random quantum event to trigger collapse. The fact we're still here might mean we're in a deeper, safer energy well than we think, but the eerie possibility lingers. Unlike asteroid impacts or supernova, false vacuum decay offers no warning, no defense. It's the ultimate existential gamble, a game of cosmic Russian roulette where every second that passes could, in theory, be the last, the only solace. If it happens, we'd never know. The end would arrive at light speed, rewriting physics so completely that concepts like before and after might not even apply in the new reality left behind. So why keep looking into the abyss? Because this isn't just doom-mongering, it's a profound question about the nature of our universe. If we're in a false vacuum, there could be deeper layers of reality waiting beneath the surface, universes with entirely different physics. That instability might even explain why our cosmos has such improbably perfect conditions for life. Like a house of cards balanced just right, maybe the only way existence can work is by teetering on the edge of collapse. Whether the vacuum stays stable or not, the theory forces us to confront an uncomfortable truth. Reality as we know it might be more fragile than we dare admit. And that changes everything, from how we weigh the risks of particle accelerators to how we measure our place in a cosmos that could, at any moment, rewrite its own rules without notice. Deep in the outer reaches of our solar system, beyond the icy orbit of Neptune, conspiracy theorists insist something massive lurks in the shadows, an undiscovered world with a chaotic, elongated path that brings it dangerously close to Earth every few thousand years. This is the legend of Planet X, also known as Nibiru, a celestial boogeyman blamed for everything from ancient mass extinctions to modern climate disasters. But where did this idea come from, and is there even a shred of scientific evidence to back it up? The story begins with Zecharia Sitchin, a controversial author who claimed to translate ancient Sumerian texts in the 1970s. According to Sitchin, these clay tablets described a rogue planet called Nibiru, home to an advanced alien race known as the Anunnaki, who supposedly engineered humanity as a slave species. He argued Nibiru follows a 3,600-year orbit, swinging perilously close to Earth each cycle and causing global upheaval. Sitchin pointed to myths of flood and fire in cultures worldwide as proof of these past encounters. Archaeologists and linguists have since debunked his translations, noting he misread Sumerian symbols and ignored historical context. But the seed was planted, and Nibiru evolved into a modern doomsday icon. Fast forward to the internet age, where fringe theorists merged Sitchin's ideas with legitimate astronomical searches for Planet X, a hypothetical large body beyond Neptune proposed to explain oddities in the orbits of distant objects. Unlike Nibiru, real Planet X hypotheses are grounded in physics, with scientists like Caltech's Konstantin Batygin using mathematical models to predict a possible Planet 9 10 times Earth's mass. But conspiracy forums twisted these studies, claiming NASA was hiding Nibiru's approach. Every blurry photo of lens flares or image artifacts became proof of the hidden planet, while doomsayers set ever-shifting dates for its catastrophic return. The scientific rebuttals are straightforward. An object with Nibiru's alleged size and orbit would be brighter than Mars in our sky long before arrival, visible to backyard telescopes worldwide. Gravitational perturbations would have been detected in the orbits of known planets centuries ago, and the idea that governments could silence every astronomer on Earth is laughable. You can't hide a celestial bulldozer plowing through the solar system. Yet the myth persists, mutating with each passing disaster. Climate change, earthquakes, even pandemics get blamed on Nibiru's invisible influence, a cosmic scapegoat for humanity's fears. What makes this theory so enduring isn't the shaky evidence, it's the psychology behind apocalyptic thinking. People have always sought patterns in chaos, and Nibiru offers a tidy explanation for random tragedies. It's also a narrative of hidden knowledge, flattering believers with the illusion they see truth others ignore. When the next doomsday date passes uneventfully, the goalposts simply move, keeping the myth alive indefinitely. But here's the twist: while Nibiru is almost certainly fantasy, the real hunt for Planet 9 continues. Batygin's team tracks icy objects in the Kuiper belt with odd, clustered orbits that suggest a distant gravitational shepherd. If found, it would be a monumental discovery, just not the fiery destroyer of legend. Perhaps that's the real lesson of Nibiru. Our universe is strange enough without inventing catastrophes. The unknown will always tempt us with stories, but science keeps us grounded in what's actually out there, waiting to be found. The moon hangs in our sky like a silent sentinel, its cratered face watching over Earth for billions of years, or so we've been told. But what if our closest celestial neighbor isn't just a lifeless rock? What if it's something far stranger, an artificial construct, a hollow relic, even an ancient spacecraft parked in orbit around our planet? This is the spine-tingling premise of the moon matrix theory, a web of ideas suggesting humanity's relationship with the moon isn't what it seems. The whispers began with the Apollo missions. Astronauts reported bizarre phenomena, unexplained flashes of light, strange metallic vibrations, even muffled radio transmissions that shouldn't have been possible. Conspiracy theorists seized on these anomalies, pointing to the moon's oddly precise orbit and unnerving symmetry. Unlike every other natural satellite in the solar system, our moon doesn't rotate chaotically. It's tidally locked, always showing Earth the same face, as if positioned deliberately. Even more suspicious, its size and distance create near-perfect solar eclipses, a cosmic coincidence so improbable, some argue it can't be accidental. Then there's the moon's composition, far less dense than Earth, with seismic readings from Apollo-era experiments suggesting it might be partially hollow. When NASA deliberately crashed the lunar module into the surface in 1969, seismometers recorded vibrations lasting over an hour, leading one scientist to quip it rang like a bell. Mainstream explanations point to a porous, fragmented crust, but fringe researchers counter with something wilder, a hollow shell, perhaps even a metal-rich interior hidden beneath a thin layer of dust. Ancient texts add fuel to the fire. From Babylonian myths describing a second moon to tribal legends warning that the moon wasn't always there, cultures worldwide hint at a time before our satellite existed. The Dogon people of Mali, renowned for their inexplicable astronomical knowledge, claimed their ancestors were visited by beings from a moon-like star long before telescopes could reveal its cratered surface. Coincidence or fragments of a forgotten truth? Skeptics brush it all off as cherry-picked data and wild speculation. They argue the moon's orbit, while precise, fits known celestial mechanics, and its density anomalies align with planetary collision models. As for the Apollo anomalies, equipment glitches and the harsh lunar environment explain most of them, but the questions linger. Why have no major lunar missions returned in over 50 years? Why do some NASA photos appear to show unnatural structures, like the infamous shard or tower spotted in lunar orbiter images? Whether the moon is a natural wonder or something more sinister, one thing's clear: it holds mysteries we've only begun to scratch. And until we go back, dig deeper, and listen to that echoing bell once more, the whispers of the moon matrix will keep us looking up, wondering what's really watching us from the dark. Could the universe be awake, not just in the poetic sense of swirling galaxies and pulsing stars, but in a literal, electrifying way, a cosmos crackling with some form of raw, unfiltered awareness? This is the radical heart of panpsychism, the theory that consciousness isn't a fluke of biology but a fundamental feature of reality itself, woven into the fabric of space-time like gravity or light. Forget the idea that your mind is just a byproduct of neurons firing. What if every atom, every quark, every ripple in the quantum foam carries a whisper of experience, and the universe itself is one vast thinking thing? The roots of this idea stretch back further than you might think. Physicist Arthur Eddington, who famously confirmed Einstein's theory of relativity in 1919, argued that the universe's structure hints at something deeper. He pointed out that the laws of physics seem strangely mind-friendly, fine-tuned to allow not just life, but the emergence of self-reflective thought. To Eddington, this wasn't coincidence, it was a clue. If consciousness is baked into reality's blueprint, then stars might not just burn, they might feel their own heat in some ineffable way. The cosmos isn't a cold machine. It's a symphony of subjective experience, with every particle playing its note. Modern thinkers like neuroscientist Giulio Tononi have taken this further with integrated information theory, which quantifies consciousness not by brain matter, but by how systems process information. Under IoT, even a humble thermostat could possess a tiny spark of experience if its components interact in the right way. Scale this up to galaxies and black holes, and suddenly, panpsychism isn't just philosophy, it's a testable framework. Some versions of the theory even suggest that the universe's structure, its tangled webs of dark matter, its quantum entanglements, resembles a neural network on a cosmic scale. Picture the Milky Way as a single neuron in a mind too vast to comprehend. But how could scattered atoms think? Panpsychists propose that consciousness operates like mass or charge, a basic property that combines and amplifies in complex systems. Just as hydrogen and oxygen merge to create water's wetness, simple particles might merge their micro-experiences into the rich inner lives of animals or humans. The difference isn't kind but degree. This sidesteps the hard problem of consciousness, how subjective experience emerges from mere matter, by arguing it was never absent to begin with. Critics pounce on the gaps. If rocks have inner lives, why don't they protest when split by hammers? If stars feel, what does supernova pain resemble? Skeptics argue panpsychism merely relabels mystery without explaining it. Others counter that human-like awareness is just one flavor of experience. A star's thoughts might be as alien to us as color is to a blindworm. Yet the theory's implications are too profound to dismiss. If true, it means the universe isn't just observed, it's observing. the night sky isn't a passive canvas, it's a living tapestry of sensation. And when we peer through telescopes, we're not just explorers, we're the universe awakening to itself piece by piece. Whether poetry or physics, that's an idea that lingers long after the stars fade from view. We think we know what life looks like: carbon-based, water-dependent, thriving on sunlight or chemical energy. But what if life isn't limited to the thin slice of reality we can see and touch? Enter the most elusive possibility of all dark matter life. Not organisms hiding in shadows, but beings made of the invisible stuff that outweighs visible matter 5 to 1, woven from particles that pass through our bodies like ghosts every second without us noticing. If life can emerge from ordinary atoms, why not from the mysterious substance binding the cosmos together? The math alone is staggering. Dark matter isn't just some hazy background presence. It forms vast, intricate structures called halos around galaxies, spinning in gravitational webs we barely understand. While normal matter clumps into stars and planets, dark matter flows like an unseen ocean, its particles barely interacting with anything, including each other. That's the first hurdle. Life as we know it requires interaction, atoms bonding, energy exchanging. How could complexity arise from particles that barely acknowledge one another's existence? Some physicists propose that dark matter isn't uniform. Just as our universe has protons, electrons, and quirks of quantum behavior, dark matter might have its own rich taxonomy, different flavors of particles with unique forces governing them. A hypothetical dark electromagnetism could allow dark matter atoms to form, creating chemistry alien to anything we've imagined. Picture a life form whose cells are held together not by molecular bonds, but by whispers of dark energy, their bodies as permeable as mist yet structured by rules we can't fathom. Then there's scale. If dark matter life exists, it might operate on timelines and sizes beyond human comprehension. A single thought in a dark matter being's mind could take millennia, their civilizations rising and falling in the time it takes a star to blink. They might perceive gravity as we perceive light, seeing the universe through ripples in space-time rather than photons. And if they're out there, we'd never know, not because they're hiding, but because our realities are so fundamentally misaligned, we're like shadows passing through each other in the dark. But here's the spine-tingling twist. Some theories suggest dark matter life isn't just separate from us, it might be right under our noses, literally. If certain dark matter particles occasionally interact with normal matter, these beings could exist alongside us, their cities floating through ours like overlapping dimensions. You might be standing in the heart of a dark matter metropolis right now, oblivious to towers of invisible architecture towering miles overhead. Critics argue this is pure speculation, and they're right, there's zero evidence. Yet the universe has surprised us before. Every time we've assumed life must follow our rules, from extremophiles thriving in nuclear reactors to tardigrades surviving space vacuum, nature laughs and shows us otherwise. Dark matter life forces the ultimate question: what really defines alive? If consciousness can emerge from quantum vibrations in a 3-pound brain, who's to say it can't emerge from the dance of particles we've yet to even detect? The eerie truth is, we may never know. Dark matter could be teeming with civilizations vastly older and stranger than our own, and we'd never hear their songs or see their art. But that's the beauty of the cosmos. It reminds us how small our perch really is. After all, if 95% of the universe is invisible to us, what else might be out there, living in the dark? You've heard the stories, misremembered movie quotes, logos that never existed, entire events that half the population swears happened differently. This eerie phenomenon, dubbed the Mandela effect, feels unsettling enough when it's about childhood books or celebrity deaths. But what if it's not just faulty memory? What if some of these collective false memories are cosmic glitches, evidence of parallel universes brushing against ours, or fractures in the simulation we call reality? Take the famous case of the Berenstain Bears. Millions insist the beloved book series was originally spelled Berenstein with an E. The sheer volume of identical false memories suggests something stranger than forgetfulness. Some researchers propose quantum entanglement between parallel worlds, moments where timelines briefly overlap, leaving fragments of alternate histories in our minds. Imagine two rivers flowing side by side. If they occasionally splash into each other, droplets from one could land in the other. In this model, a version of reality where the name was Berenstein might have momentarily intersected with ours, imprinting its truth onto our collective consciousness before slipping away. Now stretch that idea to space. Astronomers have documented anomalies where celestial objects appear to shift position or brightness in historical records, defying conventional explanations. In 1572, the astronomer Tycho Brahe observed a supernova so bright it was visible in daylight. Yet modern analysis suggests its remnant shouldn't match that intensity, as if the event itself was different in our past. Could this be a Mandela effect on a galactic scale? If parallel universes occasionally bleed into each other, perhaps even stars aren't immune to these ripples of altered memory. The simulation hypothesis adds another layer. If our universe is a digital construct, glitches in its code might explain why groups misremember the same details. Think of a video game where a texture fails to load properly. Players might see a placeholder version until the system corrects itself. In this scenario, the Berenstein spelling could have been a temporary rendering error later patched by the simulation's operators, leaving only traces in human recollection. This would make the Mandela effect not a quirk of psychology, but a digital artifact, a cosmic typo in the script of reality. Critics argue that human memory is inherently fallible, shaped by suggestion and pattern recognition. We mishear names, conflate similar images, and reinforce each other's errors until fiction feels like fact. But the persistence of certain false memories, especially among people with no prior connection, hints at something deeper. Why would thousands independently recall the same non-existent scene from Star Wars or the same distorted geography of South America? The most chilling possibility. These effects might not be random. If parallel universes or simulations exist, their interactions could follow patterns we don't yet understand. Certain memories could be hotspots, portals where realities collide most often. The next time you hear someone swear Saturn's rings used to be thicker or the moon was once brighter, consider this: they might not be wrong. They might just remember a version of the cosmos that no longer exists or one that never did. Nikola Tesla heard it first, a rhythmic signal cutting through the static of his Colorado Springs lab in 1899. He was convinced these weren't natural radio waves but deliberate transmissions, possibly extraterrestrial in origin. Decades later, amateur radio operators stumbled onto mysterious echoes of their own signals bouncing back from space, as if something unseen was reflecting them. By the 1950s, newspapers ran headlines about a mystery satellite circling Earth, its origins unknown. Thus began the legend of the Black Knight, an alleged alien probe silently watching us from orbit for thousands, maybe even millions of years. The mythos snowballed with grainy photographs and declassified documents. One infamous image, snapped during a 1998 space shuttle mission, appears to show a jagged, asymmetrical object hovering against the curvature of Earth. UFO enthusiasts claim this is the Black Knight, a hulking, ancient artifact of unknown design. Others point to radar anomalies from the early days of spaceflight, when operators tracked unexplained objects in polar orbits years before Sputnik. How could something be circling Earth before humans even dreamed of launching satellites? Then there's the supposed connection to ancient civilizations. Some theorists claim that 12,000 years ago, star maps drawn by early humans like the Dogon tribe's precise knowledge of Sirius were guided by this orbiting sentinel. A handful even argue the Black Knight isn't just watching, it's communicating. They cite the WOW signal, a powerful, unexplained radio burst detected in 1977, or the strange, long-delayed echoes of radio waves that return seconds or minutes after transmission, defying physics as we know it. But here's where skepticism crashes the party. The Black Knight photo, NASA confirms it's a thermal blanket lost during a spacewalk, those pre-Sputnik radar blips. Likely military experiments or natural phenomena like plasma disturbances and Tesla's signals. Modern analysis suggests he was probably picking up pulsars distant, rapidly spinning neutron stars that emit regular radio pulses. Even the star map connections crumble under scrutiny, with anthropologists noting that ancient astronomical knowledge, while impressive, often gets exaggerated in retellings. Yet the legend endures, fueled by secrecy around early space programs and the tantalizing "what if?" What if there's a shard of truth buried under the hype? The universe is older than our ability to comprehend. If a civilization even slightly more advanced than ours existed a billion years ago, could they have left artifacts drifting in the cosmic backwaters? The Black Knight might be a mash-up of misunderstandings and myths, but the question it raises lingers like static in the void. Are we truly alone or just not looking hard enough? Perhaps the most fascinating part isn't whether the Black Knight is real, but why we want it to be. The idea of an ancient witness, a silent observer from the stars, speaks to something primal in us, a longing to be seen, remembered, or maybe even warned. In the end, the Black Knight isn't just a satellite. It's a mirror reflecting our hopes, fears, and the unshakable sense that the cosmos holds stories we've only begun to imagine. The Red Square Nebula shouldn't exist, at least not looking like that. Nestled in the constellation Serpens, this cosmic oddity is one of the most perfectly geometric structures ever spotted in space. Unlike the usual billowing clouds of gas and dust that form most nebulas, this one presents itself as a near-perfect square, with crisp, almost artificial-looking edges that defy the chaotic nature of star death. When astronomers first discovered it in 2007, the images seemed too precise, too engineered, sparking whispers of something far stranger than a natural celestial formation. Could this be evidence of intelligence at work, a megastructure built by an advanced civilization, like a Dyson sphere caught mid-construction? The conventional explanation involves a rare alignment of stellar winds. At the heart of the Red Square lies MWC 922, a massive star nearing the end of its life. As it ejects material, twin cones of gas shoot out in opposite directions, and from our vantage point, these cones create the illusion of a square. It's like looking at two ice cream cones placed tip to tip. Their edges form a diamond shape, and with precise symmetry, that diamond can appear uncannily square. Supporters of this model point to other bipolar nebulas, like the stunning Hubble images of the Red Spider Nebula, which show similar, if less perfect, geometric tendencies. But here's where things get weird. The Red Square's symmetry is too precise. Natural processes rarely produce such razor-sharp angles without some form of turbulence or asymmetry. Even more puzzling are the concentric rings within the nebula, resembling ripples in a pond, except these ripples are evenly spaced, as if something or someone deliberately stamped them into existence. Some researchers argue that if an advanced civilization were building a Dyson sphere, a hypothetical structure designed to harness a star's energy, they might start by constructing scaffolding or reflective panels in staggered layers. The Red Square's nested squares could, in theory, be the skeletal framework of such a project, visible only because it's incomplete. Then there's the light. The nebula's eerie red glow comes from excited hydrogen molecules, but the way that light is polarized, aligned along specific planes, doesn't quite match typical stellar radiation patterns. Unusual polarization can sometimes indicate artificial manipulation, like light bouncing off structured surfaces rather than scattering through chaotic gas clouds. Of course, skeptics counter that unusual doesn't mean unnatural. The universe is full of phenomena we don't yet understand, from magnetars to fast radio bursts, and jumping to aliens every time we hit a cosmic puzzle is a dead end. Yet the mystery lingers. If the red square is natural, it's a 1 in a billion fluke, a cosmic origami project folded by sheer chance. If it's not, it could be the most profound discovery in human history, a billboard in the void, silently announcing we're not alone. Until we send probes or develop telescopes capable of resolving its structure in finer detail, the red square will remain a Rorschach test for the cosmos. We see what we want to see, a trick of the light or the shadow of something watching back. Somewhere beyond the stars, in the direction of the constellations Centaurus and Hydra, an invisible force is reeling in entire galaxies like fish caught in a cosmic net. This is the Great Attractor, a gravitational anomaly so powerful it's dragging the Milky Way and millions of other galaxies toward it at 14 million miles per hour. Yet despite its immense influence, we've never actually seen it. Our view is blocked by the Milky Way's own galactic bulge, a thick band of stars, gas, and dust called the zone of avoidance, where the density of material is so high, it's like trying to peer through a blackout curtain. The mystery began in the 1970s when astronomers noticed something bizarre about the universe's large-scale flow. While the expansion of space should send galaxies drifting apart, entire clusters, including our own, were moving toward a specific patch of sky. This wasn't just random motion. Something with the mass of tens of thousands of Milky Ways was pulling us in. Early estimates placed the Great Attractor about 250 million light-years away, but the true nature of this gravitational behemoth remained obscured quite literally by our galaxy's dusty veil. For decades, astronomers could only guess what lay behind the zone of avoidance. Then, in the 21st century, new tools like infrared and X-ray telescopes began piercing the cosmic fog. What they found was even stranger than expected. The Great Attractor isn't a single massive object, it's a colossal knot in the cosmic web, a confluence of galaxy superclusters with the Norma cluster at its heart. This region, dubbed the Laniakea supercluster, is a sprawling metropolis of galaxies spanning 500 million light-years, with the Great Attractor acting as its gravitational center of mass. Yet the plot thickens. Recent observations suggest this titanic structure might itself be moving, pulled toward an even larger and more distant anomaly, the Shapley Attractor, a supercluster of galaxies 800 million light-years away. It's as if the universe is a Russian nesting doll of gravitational mysteries, each one leading to something bigger and more enigmatic. The implications are staggering. If the Great Attractor is just one link in a chain of cosmic currents, what does that say about the forces shaping the universe? Some theorists speculate that these flows could be remnants of the Big Bang's primordial energy, frozen into the fabric of space-time. Others wonder if we're witnessing the influence of dark energy or something even more exotic. One thing's certain, the Great Attractor forces us to confront how little we truly grasp about the cosmos. Even the mightiest structures we've discovered might just be specks in a larger, unseen tapestry, one we're only beginning to unravel. In 1972 and 1973, NASA launched the Pioneer 10 and 11 probes, twin spacecraft designed to explore the outer solar system and beyond. These rugged explorers became the first human-made objects to journey past Mars, through the asteroid belt, and into the realm of the gas giants, beaming back breathtaking images of Jupiter and Saturn. Yet long after their primary missions ended, as the Pioneers drifted toward interstellar space, something strange happened. Their trajectories began deviating from the precise calculations of NASA engineers. The probes were slowing down not from friction or solar wind, but as if an invisible hand were gently tapping the brakes, altering their course by 300 miles every year. This tiny but persistent discrepancy became known as the Pioneer anomaly, a cosmic mystery that would baffle scientists for decades. At first, researchers assumed the deviation was due to mundane causes, maybe a fuel leak, or the faint push of escaping heat from the probe's nuclear power sources. But as the years passed and the anomaly persisted, even the most meticulous calculations couldn't account for the drag. The pioneers weren't just off by a little. They were defying Newton's laws of motion in a way that suggested either a flaw in our understanding of gravity or the presence of something unseen. Some theorists proposed exotic explanations like the influence of dark matter. If our galaxy is embedded in a halo of invisible particles, as most cosmologists believe, could these probes be plowing through a thicker patch of it, creating a subtle but measurable drag? Others wondered if Einstein's general relativity needed tweaking at cosmic scales, or if an unknown force was at work in the depths of space. Then there were the wilder ideas. What if the anomaly wasn't a natural phenomenon at all? A handful of researchers dared to speculate that the pioneers might have encountered something artificial, an undetected gravitational lens, a relic of alien engineering, or even a ripple in space-time left by a long-gone civilization. These notions veered into fringe territory, but they underscored just how perplexing the pioneer anomaly truly was. Here was a deviation so small it could have been dismissed as a rounding error, yet it hinted at gaps in our grasp of physics that might rewrite the rules of the cosmos. The mystery finally unraveled, at least partially, in 2012, when a team of researchers painstakingly reconstructed the probe's heat emissions. It turned out the anomaly wasn't caused by dark matter or new physics, but by something far more mundane: thermal radiation. As the pioneers' radioactive power sources decayed, heat radiated unevenly from their bodies, creating a faint but constant push in the opposite direction of the sun. This thermal recoil force was enough to account for the drift, case closed, or so it seemed. Yet even now, some scientists argue the explanation isn't entirely satisfying. The thermal model fits most of the data, but not all of it. And if heat alone explains the anomaly, why haven't other spacecraft like Voyager or New Horizons shown similar deviations? The truth might lie somewhere in between, a mix of known physics and subtle, overlooked factors. The Pioneer anomaly serves as a humbling reminder: space is never as empty or predictable as we assume. Even in the void between stars, the universe finds ways to surprise us, whispering secrets we're only beginning to decode. And sometimes the smallest anomalies lead to the biggest questions about what we know, what we don't, and what might still be hiding in the dark. In October 2017, astronomers spotted something unprecedented: a visitor from beyond our solar system, tumbling past the sun at blistering speeds. Named Oumuamua, Hawaiian for scout or messenger, this interstellar interloper defied all expectations. Unlike comets or asteroids we've seen before, it had no visible tail of gas or dust, yet it accelerated as it moved away from the sun, as if pushed by an unseen force. Its shape was even stranger: long and cigar-like, spinning end over end, unlike the lumpy space rocks orbiting our sun. But the real controversy began when Harvard astrophysicist Avi Loeb raised a startling possibility. What if Oumuamua wasn't just a quirky rock? What if it was a piece of alien technology, a light sail, a probe, or even a derelict spacecraft? Mainstream science quickly offered alternatives. The acceleration could be explained by outgassing hidden jets of material evaporating from Oumuamua's surface, acting like tiny thrusters. Its odd shape might just be a fragment from a larger body, sheared off in some ancient cosmic collision. After all, this was our first glimpse of an object from another star system. Expecting it to behave like local asteroids was like assuming every country's trees grow the same way. But Loeb pushed back. Outgassing should have left detectable gas or debris, yet none was found, and the object's brightness varied tenfold as it spun, suggesting an extremely elongated structure, almost like a flattened pancake. Natural debris rarely forms such perfect, slim profiles. Then there was the math. Loeb's calculations showed Oumuamua's acceleration perfectly matched what you'd expect from solar radiation pushing on a thin, lightweight object, exactly the properties of a light sail, a theoretical propulsion system that uses sunlight for momentum. Human projects like Breakthrough Starshot are already developing similar technology to send tiny probes to nearby stars. Could Oumuamua be someone else's version of that, a messenger intentionally or accidentally sent our way? Critics weren't convinced. They argued extraordinary claims require extraordinary evidence, and Oumuamua's oddities, while fascinating, could still fit within known physics. Its surface might have been covered in solid hydrogen or nitrogen ice, materials that could vaporize without leaving obvious traces. Or perhaps it was a fractal-like dust bunny of porous material, giving it bizarre aerodynamics. The biggest sticking point we'll never know for sure. Oumuamua is now beyond the reach of our telescopes, streaking toward the outer solar system without a trace. Yet the debate lingers, forcing us to confront an uncomfortable truth. When the next interstellar visitor arrives, will we dismiss its quirks as natural, or risk missing the signature of intelligence beyond Earth? Loeb's stance isn't just about one object, it's a challenge to science itself. In a universe that's repeatedly surprised us, from quantum entanglement to black holes, why assume we've already imagined every possible form life or technology could take? Whether Oumuamua was alien or just oddly shaped ice, it's a reminder. Sometimes the most important discoveries aren't the answers we find, but the questions we dare to ask. The night of August 15, 1977, started like any other at Ohio State University's Big Ear radio telescope. Volunteers were scanning the skies for signs of extraterrestrial intelligence, methodically recording static and cosmic noise. Then at 10:16 p.m., the machine spat out a signal so powerful, so perfectly aligned with what scientists predicted an alien broadcast would look like, that astronomer Jerry Amon circled it in red pen and scribbled, "Wow." Next to the data, that single, fleeting burst lasting just 72 seconds became the most tantalizing maybe in the history of the search for extraterrestrial intelligence. And then, nothing. Despite decades of follow-up observations, the signal never repeated, leaving behind one burning question: what really caused the wow signal, and why did it vanish without a trace? What made this blip special wasn't just its strength, 30 times louder than background noise, but its frequency. The signal hit 1420 MHz, a quiet spot in the radio spectrum where cosmic interference is minimal. Natural sources like pulsars or quasars typically broadcast across multiple frequencies, but this was laser-focused, like a cosmic whistle in the dark. Even stranger, it followed the exact pattern scientists had theorized an alien transmission might use: narrowband, unmodulated, and drifting slightly in frequency as Earth's rotation altered the telescope's reception. It was as if the universe had handed us a textbook example of an intentional signal, then yanked it away before we could respond. The leading natural explanation points to hydrogen clouds or comets. In 2017, researchers proposed that two passing comets, undetected at the time, might have emitted hydrogen gas that the Big Ear picked up. The timing matched. Both comets were in the right region of space, but critics shredded the idea. Comets release broad-spectrum radio noise, nothing like the wow signal's precision. Others suggested a rogue satellite or military transmission, but no records show any man-made objects operating on that frequency at the time. The more plausible yet unsettling possibility: the signal was exactly what it seemed, a deliberate, one-time broadcast, perhaps from a civilization that didn't stick around to chat. Here's where the mystery deepens. The wow signal originated near the constellation Sagittarius, in a star-rich region where astronomers have since identified several potentially habitable exoplanets. One particularly intriguing candidate sits around a Sun-like star just 1,800 light-years away. close enough that a sufficiently advanced civilization could have beamed a message we'd catch now. But if so, why not transmit continuously? Some theorists speculate it might have been a targeted probe like our own Arecibo message, fired off randomly and never repeated. Others imagine a beacon sweeping the galaxy like a lighthouse, briefly illuminating Earth before spinning away. Or perhaps the signal wasn't meant for us at all, just a fragment of alien chatter intercepted by chance, like overhearing one word in a conversation we'll never fully grasp. The most haunting explanation of all is the simplest: we missed our chance. The big ear could only observe one spot at a time, and by the time Eamon alerted other telescopes, the signal was gone. Modern projects like Breakthrough Listen now scan millions of frequencies simultaneously, but space is vast and patience is thin. The WOW signal remains a cosmic tease, a single note in what might be a symphony we're no longer tuned to hear. Whether it was aliens, a freak cosmic event, or something beyond our current understanding, one thing's certain: that lonely red WOW on a printout changed how we look at the sky, reminding us that sometimes the most profound messages come without a return address. Venus-Earth so-called twin has long been dismissed as a hellscape, a toxic, pressure-cooked wasteland where lead melts on the surface and sulfuric acid rains from the sky. But in 2020, a bombshell announcement turned planetary science on its head. Astronomers detected phosphine gas in Venus' upper atmosphere, a molecule that on Earth is almost exclusively produced by living organisms. Suddenly, the idea of life floating in Venus clouds didn't seem so far-fetched. Could Earth's twisted sister harbor microbes high above her deadly surface, thriving in temperate cloud layers where temperatures and pressures eerily mirror our own planet? The discovery began with Jane Greaves and her team at Cardiff University, who pointed the James Clerk Maxwell telescope in Hawaii toward Venus, expecting to find nothing more than the usual cocktail of carbon dioxide and sulfuric acid. Instead, their instruments picked up the spectral fingerprint of phosphine, a compound made of one phosphorus atom and 3 hydrogen atoms. On Earth, phosphine is linked to anaerobic bacteria in swamps and the guts of animals, or to industrial processes. It's not something that should form spontaneously in Venus' oxidizing atmosphere. The numbers were shocking: 20 parts per billion, a concentration that defied non-biological explanations. When the team double-checked with the more powerful ALMA array in Chile, the signal held. The universe, it seemed, had thrown us a curveball. Of course, extraordinary claims demand extraordinary scrutiny. Almost immediately, other researchers pushed back. Some argued the phosphine signal could be sulfur dioxide, a common Venusian gas with a similar spectral signature. Others suggested volcanic activity, though Venus volcanoes, while active, shouldn't produce phosphine in such quantities. Then came the real blow. A reanalysis of the ALMA data found calibration errors that might have skewed the results. By 2021, the original detection was in doubt, with some scientists calling it a false alarm. But the story didn't end there. In 2023, new studies reignited the debate. Independent teams reprocessed the data, accounting for the earlier errors, and astonishingly still found traces of phosphine, though at lower levels. Meanwhile, planetary scientists revisited old data from NAS, a pioneer Venus mission in the 1970s, uncovering hints of chemical imbalances in the clouds that could support microbial metabolisms. Venus' atmosphere, it turns out, has unexplained dark patches that absorb ultraviolet light, a phenomenon some compare to algal blooms on Earth, the most tantalizing possibility. Acid-resistant microbes, similar to extremophiles in our own acidic hot springs, could be floating 50 kilometers above Venus' surface. At that altitude, temperatures hover around 30 degrees Celsius with pressures akin to Earth sea level. These hypothetical Venusians wouldn't need oxygen or water, just droplets of sulfuric acid as their life-giving solvent. They might even evolve a bizarre photosynthesis-like process, using the planet's constant ultraviolet glare as an energy source. Skeptics remain unconvinced, and rightly so. Without a direct sample, the phosphine debate is stuck in limbo, but the implications are too staggering to ignore. If life exists on Venus, it suggests biology isn't just a fluke of Earth's Goldilocks conditions, it's a cosmic imperative, capable of taking root even in the most hostile niches. And if it's not life, then Venus is hiding geological or chemical processes far stranger than we've ever imagined. Either way, the answer forces us to rethink not just our nearest planetary neighbor, but the very boundaries of what we call alive. The clouds of Venus, it seems, hold mysteries that refuse to dissolve no matter how much acid we throw at them. In July 1976, NASA, a Viking 1 orbiter, was mapping the surface of Mars when it captured something that would ignite decades of controversy. A mile-long mesa in the Cydonia region that bore an uncanny resemblance to a human face. The face on Mars image, with its symmetrical eye sockets, nose, and even what looked like a headdress, sent shockwaves through the public imagination. Was this proof of an ancient Martian civilization, a monument carved by intelligent beings long before humans walked the Earth? The grainy black and white photo became a Rorschach test for conspiracy theorists, ufologists, and even mainstream scientists, each projecting their own interpretations onto those shadowy Martian features. NASA's initial caption for the image was dry and clinical. The huge rock formation resembles a human head, but the press ran wild with it, splashing headlines about alien artifacts across tabloids and even serious news outlets. The timing couldn't have been more perfect. Just a year after the cult classic Ancient Astronauts theory had been popularized by Erich von Däniken's book Chariots of the Gods, which argued that extraterrestrials influenced early human civilizations. Now here was what looked like a smoking gun, evidence that the same beings might have left their mark on Mars too. The face became a cultural phenomenon, inspiring everything from sci-fi novels to episodes of The X-Files, all asking the same eerie question: who built this? But science, unlike speculation, demands repeatable evidence. When NASA Mars Global Surveyor returned to Cydonia in 1998 and 2001 with vastly superior cameras, the face lost its mystique. High-resolution images revealed a brutally ordinary but heavily eroded by wind and time, with none of the precise symmetry the original photo had suggested. The illusion was a classic case of pareidolia, the human brain's tendency to see familiar patterns in random shapes, like animals in clouds or the man in the moon. Shadows that had once looked like carved pupils were just pits in the rock. The headdress grooves were nothing more than natural fractures, case closed, or so NASA thought. Yet the conspiracy refused to die. Skeptics argued the new images were suspiciously low contrast, as if someone had deliberately blurred them to hide the truth. Others claimed the real face was buried underground, or that NASA had digitally altered the photos to suppress the discovery. The debate split into two irreconcilable camps: those who trusted the scientific process and those who believed in a cover-up. Even when later missions like the European Space Agency's Mars Express and NASA, a Mars reconnaissance orbiter, delivered crystal-clear 3D topographical maps of Cydonia, showing a thoroughly unremarkable hill, true believers held firm. For them, the face wasn't just a rock, it was a symbol of humanity's reluctance to accept that we might not be alone. What makes the Mars face conspiracy so enduring isn't the geological facts, but the deeper questions it forces us to confront. Why are we so desperate to find meaning in randomness? Is it hope, a longing for cosmic neighbors, or arrogance, the assumption that intelligence must leave monuments as we do? The face may be an illusion, but the fascination it sparked reveals something profound about us. After all, in a universe of infinite possibilities, the strangest artifact might not be a rock on Mars, but the human mind that insists on seeing a face where none exists. Imagine a spinning carousel with most of its horses missing, yet somehow it whirls just as fast as one packed with riders. That's the cosmic conundrum posed by NGC 1052-DF2, a galaxy that defies one of modern astronomy's most fundamental rules. Discovered in 2018, this ghostly collection of stars floats 65 million light-years away with almost no dark matter, the invisible glue thought to hold galaxies together. According to every established model of galaxy formation, this shouldn't be possible. Dark matter isn't just a minor ingredient. It's supposed to be the cosmic scaffolding that makes galaxies possible in the first place. So how does this galactic rebel exist, and what does its defiance mean for our understanding of the universe? The discovery sent shockwaves through astrophysics because dark matter has been the cornerstone of cosmology for decades. We've built entire theories around its gravitational pull, using it to explain why galaxies don't fly apart as they spin and how cosmic structures formed after the Big Bang. Then along comes NGC 1052-DF2, a wispy, see-through galaxy where stars move at a sluggish pace, betraying none of the hyperactive motion dark matter should cause. Measuring its rotation, researchers expected to find the usual dark matter halo, but the numbers were startling. This galaxy's mass matched its visible stars almost perfectly, leaving no room for the unseen stuff we thought was universal. Critics scrambled for explanations. Maybe we're misjudging the galaxy's distance, skewing the calculations. Perhaps tidal forces from a neighboring galaxy stripped away its dark matter like a cosmic thief. But follow-up studies only deepened the mystery. The team found another dark matter-deficient galaxy, NGC 1052-DF4, nearby, suggesting this wasn't a fluke but a pattern. Even more bizarre, these galaxies are ultra-diffuse, with stars spread so thinly you could fly through them for light years without spotting a single sun. If dark matter isn't propping them up, what keeps their stars from drifting into the void? The implications are tectonic. If such galaxies are common, it could mean dark matter isn't as indispensable as we thought, or that it interacts in ways we've never imagined. Some theorists propose alternative gravity theories, like modified Newtonian dynamics, which tweak the laws of physics to eliminate the need for dark matter altogether. Others suggest these outliers are failed galaxies that formed in rare pockets where normal matter clustered without dark matter's help. Then there's the wild card. What if dark matter isn't a single substance, but a family of particles with diverse behaviors? Maybe NGC 1052-DF2's dark matter is just different, like a shadow that refuses to follow its owner. For now, the galaxy remains a tantalizing outlier, a cosmic heretic challenging orthodoxy. Every time we think we've pinned down the universe's rules, something like this whispers, "You're missing the bigger picture." Whether it's a clue to dark matter's true nature or a signpost to entirely new physics, one thing's clear: the cosmos loves throwing curveballs. And the more we look, the more we realize how much we've yet to learn. Stretching across a billion light-years of cosmic emptiness, the cold spot in the cosmic microwave background isn't just a minor temperature dip, it's a yawning chasm of nothingness so vast and inexplicable. It defies everything we know about how the universe should behave. Nestled in the constellation Eridanus, this eerie patch of sky registers as a blisteringly cold anomaly in the afterglow of the Big Bang, a place where the ambient radiation is significantly colder than surrounding regions. At first glance, it might seem like a statistical hiccup in the data, except the odds of such a frigid void forming naturally are less than 1 in 50. So what carved this cosmic crater, and why does its existence hint at realities beyond our own? The leading scientific explanation pins the cold spot on a supervoid, an incomprehensibly large region of space where galaxies are mysteriously scarce. Most voids in the universe span a few hundred million light-years, but this one dwarfs them all, its edges seemingly empty of the usual cosmic scaffolding. When photons from the cosmic microwave background pass through such a void, they lose energy climbing out of its gravitational well, causing a redshift that translates into a temperature drop, a phenomenon called the integrated Sachs-Wolf effect. But here's the catch: even the largest known supervoids can't fully account for the cold spot's extreme chill. The math simply doesn't add up. This discrepancy has led some cosmologists to propose a far wilder idea. The cold spot might be a bruise from a collision with another universe. In the multiverse model, where countless bubble universes float in a higher dimensional foam, such crashes could theoretically leave imprints on the cosmic microwave background. Picture two soap bubbles gently nudging each other. The point of contact would distort their surfaces, creating a dent. If our universe collided with a neighboring one in the distant past, the energy drained from that impact zone could manifest as the cold spot we observe today. It's a radical notion, but one that aligns eerily well with the anomaly's unprecedented scale and temperature profile. Skeptics, of course, have alternative explanations. Some argue the cold spot could be a statistical fluke magnified by observational bias, a trick of the light in how we map the cosmic microwave background. Others suggest more exotic physics, like a gravitational ripple from a cosmic texture, a hypothetical defect in spacetime structure left over from the universe's violent birth. Yet none of these fully dismiss the lingering questions. Why is the cold spot so perfectly circular? Why does its temperature gradient defy conventional void models? And why do simulations of the universe's large-scale structure struggle to reproduce anything quite like it? The implications are staggering. If the cold spot truly is evidence of a multiverse, it would be the first tangible clue that our cosmos is just one bubble in an infinite froth of realities. It would mean the laws of physics we hold as universal might be local bylaws, with entirely different rules governing other universes just beyond the veil. Even if the explanation turns out to be more mundane, the cold spot's persistence forces us to confront how little we understand about the universe's architecture. After all, when a billion light-year gap in reality stares back at you cold and silent, it's hard not to wonder what else might be lurking in the shadows, waiting to rewrite the story we thought we knew. What if you could propel a spacecraft without fuel, no rockets, no exhaust, just a mysterious thrust that seems to conjure motion from nothing? This is the tantalizing promise of the M-drive, a propulsion concept so controversial it's been called the impossible engine. Conceived by aerospace engineer Roger Scheuer in the early 2000s, the M-drive looks more like a copper kitchen gadget than a revolutionary thruster, a truncated cone you could mistake for a fancy pasta pot. But inside that simple shape lies a claim that upends 300 years of physics. By bouncing microwaves around its chamber, the device allegedly generates thrust without expelling any propellant, violating Newton's third law that every action must have an equal and opposite reaction. The implications are staggering. A working M-drive could slash travel times across the solar system, enabling missions to Mars in weeks instead of months. It could theoretically reach relativistic speeds, making interstellar voyages feasible without the need for planet-sized fuel tanks. No wonder NASA Eagleworks Lab, alongside teams in China and Germany, took the idea seriously enough to test it. In 2016, their experiments seemed to confirm the impossible tiny but measurable thrust signals, as if the M-drive was pushing against the fabric of spacetime itself. The results sent shockwaves through the scientific community. Either we'd stumbled onto a physics-shattering breakthrough or something was terribly wrong with the data. Skeptics pounced immediately. Without exhaust, the M-drive appeared to be a perpetual motion machine in disguise, violating the conservation of momentum, a law so fundamental that rewriting it would unravel everything from how planets orbit to why bullets recoil. Critics argued the observed thrust was likely experimental error, thermal expansion of the device, interactions with Earth's magnetic field, or even air currents in the lab. When the German team repeated the tests in a near-perfect vacuum, the thrust vanished. NASA's own follow-up studies found that the effect diminished when accounting for all possible external forces, suggesting the initial excitement might have been premature. Yet the mystery refuses to die. Some theorists propose loopholes in known physics that could explain the M-drive's behavior without overturning Newton. One idea suggests the microwaves might interact with quantum vacuum fluctuations, a froth of virtual particles popping in and out of existence, effectively pushing off an unseen sea of energy. Another posits that the conical shape creates asymmetric radiation pressure, like a one-way valve for photons. These hypotheses remain fringe, lacking rigorous mathematical grounding, but they hint at how little we still understand about the quantum realm. What makes the M-drive debate so fascinating isn't just the science, it's the psychology of discovery. The line between crackpot invention and paradigm shift has always been blurry. X-rays were once dismissed as hoaxes. Continental drift seemed laughable until plate tectonics proved it. The M-drive forces us to confront how science grapples with anomalies. Do we dismiss them as noise or risk chasing ghosts in the hope of a revolution? For now, the consensus leans toward the former, but in a universe where dark energy accelerates expansion and particles teleport through barriers, maybe impossible is just a word waiting to be rewritten. The M-drive's greatest legacy might not be thrust, but humility, a reminder that the cosmos still holds puzzles no textbook has solved. Imagine sending a message across the universe instantly, no waiting for signals to crawl at light speed, no lag between stars. This sci-fi dream might just be possible through one of quantum mechanics' most bewildering phenomena, entanglement. When two particles become entangled, they share a ghostly connection that defies distance. Change the spin of one electron here, and its partner light years away instantly mirrors that change, as if space between them doesn't exist. At first glance, this seems like the ultimate communication hack, a cosmic Morse code tapping out messages faster than light. But here's the catch: Einstein called this spooky action at a distance. And for decades, physicists insisted it couldn't be used to send actual information. The reason: relativity's unbreakable law. Nothing, not even quantum weirdness, outpaces light speed. The heart of the problem lies in how entanglement actually works. While entangled particles do react to each other instantaneously, you can't control the state of the particle you're measuring. It's like having a pair of magical coins that always land on opposite faces when flipped, but you don't get to choose whether yours shows heads or tails. Without control over the initial state, you can't encode a deliberate message. All you see is random correlation, which only makes sense after comparing notes the old-fashioned way, slowly at light speed or below. This is why physicists long dismissed FTL communication via entanglement as fantasy. Yet recent experiments have nudged the door open, just a crack. Quantum teleportation, a process where the state of a particle is transferred to its entangled partner, shows that information can effectively jump between points without traversing the space in between. In 2017, Chinese scientists shattered records by teleporting quantum states from Earth to a satellite over 1,000 kilometers away. The key: you still need a classical signal to decode the teleported information, keeping relativity intact. But what if there's a loophole? Some theorists speculate that advanced civilizations might have found ways to exploit higher dimensions or exotic physics we haven't yet grasped, turning entanglement into a galactic internet. The implications are dizzying. If faster-than-light communication were possible, it would rewrite not just physics textbooks but the structure of reality itself. Causality, the ironclad rule that cause must precede effect, would crumble. Messages could arrive before they're sent, creating paradoxes that make time travel look straightforward. Maybe that's the universe's way of saying some doors should stay closed. Or maybe we're just scratching the surface of what quantum connections can truly do. Either way, entanglement remains one of nature's most tantalizing near misses, a whisper of instant contact forever hovering just out of reach. From the chilling possibility that our universe is a simulation to the spine-tingling idea that dark matter could harbor invisible civilizations, we've ventured through theories that stretch science to its breaking point. We've stared into the abyss of quantum immortality, where consciousness might cheat death across infinite realities, and grappled with the holographic principle, a universe where depth itself could be an illusion. We've wrestled with the cosmic silence of the Fermi Paradox, asking whether alien civilizations are hiding, extinct, or never existed at all. Each theory isn't just a wild guess, it's a challenge to our deepest assumptions about reality, proof that the universe refuses to fit neatly into the boxes we build for it. Consider the implications. If the holographic principle is true, everything you see, touch, and experience could be a two-dimensional projection from the edge of space. If the great attractor is pulling us toward something beyond our cosmic horizon, what unseen structures lurk in the void? And if Oumuamua was truly an alien artifact, how many other interstellar visitors have we missed? These ideas aren't just science fiction. They're frontiers where respected scientists dare to ask, what if we're wrong? That's the heartbeat of discovery, the courage to question even when the answers rewrite the rules. Now it's your turn. Which of these theories rocked your worldview the most? Is it the Boltzmann brain, the eerie chance that you're a momentary consciousness conjured from chaos? Or the Black Knight satellite, a silent watcher that might not exist, or might be hiding in plain sight? Drop your pick in the comments and let's geek out over the cosmos' greatest mysteries together. And if your brain's still buzzing with questions, trust us, ours are too. Hit subscribe. We're just scratching the surface of the universe's secrets, and the next revelation might be even wilder than the last. After all, in a cosmos this strange, the only limit is our imagination, and we're just getting started.